I'm on a strange road. It's anything but a racetrack. It's very narrow. There's a rock wall to one side and a sheer drop the other. Definitely not for nervous drivers. I'm in the Sonoran Desert of Arizona, and this road leads up the side of Mount Hopkins. Right on the top of the mountain, we find what looks from the distance almost like a doll's house, but which turns out to be the home of a most unusual telescope, the MMT, or Multiple Mirror Telescope. Here's the dome, under more cloud than usual, I may say. It spins round with a telescope. It goes round on rails, and these rails have to be kept clear. Snow can be a problem, and so in fact can ladybirds. On one occasion, the rotation had to be stopped while ladybirds were cleared out of the way. And here is the MMT itself. It doesn't look a bit like a telescope. It's a mass of steel wires and girders. There are 6 72-inch mirrors, which work together and make up the equivalent of a single 176-inch mirror, one of the largest in the world. But why use 6 mirrors when one will do? Well, there are 2 main reasons. First, making 6 small mirrors is a great deal easier than making one very large mirror. And secondly, cost. When the MMT was built, it cost a great deal less than a conventional 176-inch telescope would have done. The MMT has now been in action since 1979. Yet now, there's to be a radical change. The 6 72-inch mirrors are to go, to be replaced by a single 256-inch or 6.5-meter mirror. Well, has it been a real success?
I think the answer, Patrick, is it's been an unmitigated success. There are many things that the MMT wanted to do, and many of which we have managed to do in our history. First of all, the site itself is a very excellent site for a telescope, although looking at the clouds behind me today, you wouldn't necessarily know that. 1 month or 2 months a year, we have the monsoon pattern that hits Arizona, and in fact, we shut down nighttime operation, as do most of the observatories in Arizona, during the month of August, which happens to be when we are here. The seeing at the site has been extraordinarily good. That is, the quality of the star images has been extraordinarily good, so we've been very pleased with that. And most importantly, the amount of time we have lost to any technical problems with the telescope has been very, very minimal.
Is there a real problem nowadays with aligning the mirrors?
No, that's been evolutionarily one of the more difficult things to do with the MMT. We began with a laser co-alignment system for the telescope, whereby an artificial star was generated at the center of the structure and sent out to each of the 6 mirrors. For a number of reasons, this did not work. And early in the 1980s, that scheme was abandoned. One of the more comical reasons it didn't work, since we've talked about insects, is that moths interrupting the beam at night would shut down the laser co-alignment system. And in fact, that got to be a real problem. Moth recognition on the computers was a real difficulty. But over and above that rather comical reason, there were seemingly fundamental limitations at that time. And so in the early 80s, we switched to a much more straightforward system, whereby we simply digitally record the images at the focal plane of the telescope, and there's 6, 1 from each telescope, figure out where the center of the image is electronically, and then command the secondary mirrors to bring all 6 of those images on top of each other.
I wonder if you'd now please take us through the main features of the MMT.
There are a lot of unusual things about the MMT, starting with its mirrors. The mirrors themselves were among the first actually light-weighted mirrors that were used in a large telescope. Secondly, the mount of the telescope is an altitude azimuth mount, which is, this day and age, sounds almost typical, but when the MMT was built, there was really only one other telescope in the world that was trying this of any size, and that was the Soviet 6-meter telescope. This telescope, in fact, has a tracking performance that has now become the standard against which other performances are measured throughout the world. So that was another big difference. And finally, the building itself. With the MMT, we chose to make the entire building co-rotate with the telescope. So that also was an extremely unusual feature, and that too has worked out extraordinarily well.
What are the main researches carried out with it?
I would say that some of the most important have been having to do with research on the most distant objects in the universe, which is Y1bils, or to a large extent Y1b is a very large telescope. And this means the quasars. A large amount of work has been done here on quasar research of all kinds, and in particular in research on gravitational lenses. A gravitational lens is a phenomenon that occurs when the light from a distant quasar passes some massive object in its trip from the quasar to the Earth. The massive object may be another quasar, most often it's a galaxy, and that galaxy actually distorts the image of the quasar and causes multiple images to occur.
One question I'm sure you've been asked: if the MMT had been such a success, why do you now plan to convert to a single mirror?
Well, as you can tell from my smile, it is a question I've been asked often. And really the reasoning behind it was in 1985, Roger Angel and I began discussions because it looked at that time as if his mirror manufacturing process might be a success. And it looked to me and to Roger as if very large telescopes that hitherto could not have been built could probably be built. And already there were plans on the board for building very large telescopes, so that we could see the time in not a very long time, before the end of the century, for example, that the MMT would go from being the third largest telescope in the world to something like 10th or 12th. Now that's still a respectable sized telescope at 4.5 meters, but it does mean that certain kinds of frontier research will not be able to be done on a telescope of 4.5 meters.
Of course, there are other ways of making telescopes of tremendous light grasp. Over on Mauna Kea in Hawaii, for example, there is the Keck telescope, where the mirror is made up of segments fitted together to make the correct curve. But up to now, making huge single mirrors has always been very much of a problem. But now there's a new and highly revolutionary method. Underneath the University of Arizona football stadium, there's a most unusual astronomical laboratory. It's here that the great new mirror for the telescope is being built, 6.5 meters, or 256 inches in diameter.
Well, the idea is we want to make a honeycomb that's to have both stiffness and to be lightweight, and it's made of this borosilicate glass, which we find very easy to melt. The mirror contains 10.5 tons of this glass in chunks like this. And we put these chunks of glass on top of a mold, which is the reverse of the honeycomb. And the honeycomb mold is made of aluminosilica fiber in hexagonal shapes like this one here. So these make out the hexagonal voids in the honeycomb. And there are 1,020 of them that are bolted down onto the floor of the mold. And then the glass is placed on top of these, and when it melts, it runs down the side of this mold to form the ribs of the honeycomb.
What about the rotating system?
Well, besides being a honeycomb, this is also a very fast focal ratio mirror. And so it has a quite steep sag from the center to the edge of the mirror. And to get that sag without grinding off another 10 tons of glass, which would be expensive both for grinding and for buying another 10 tons of glass, we spin the furnace, and by spinning the furnace, we form a parabolic shape on the surface. And for this mirror, a 6.5 meter with a focal ratio of 1.25, this rotation speed is 7.4 RPM. And we hold that to about 1,000th of an RPM for about 3 days while the glass is liquid.
You started making this mirror last April. How's it going?
Well, it's going quite well now. In fact, from the point of view of cooking the mirror, it's done. We cast on April 2nd and 3rd when the glass was actually molten and running down into the mold. And then the nervous part of the operation is that we have to cool at 1/8 of a degree per hour through the temperature range around 500, where the glass anneals and relaxes its stress and strain that's built up during the casting. So that was the nervous time. Now that we've finally got it down to room temperature, we don't have to watch it 24 hours a day, and we can go in and touch it and feel it and look at it and see that it looks like a quite nice honeycomb.
For this method, everything depends upon a really effective furnace. And this one's really large. You can see that from the size of the base. It can attain a temperature of well over 2,000 degrees Fahrenheit, and it can spin at up to 10 revolutions per minute. The originator of the spin method is Dr. Roger Angel. It was thought for many years that single mirrors had reached their maximum size. What made you think they hadn't?
Well, normally when you make a single mirror, in order to get it stiff enough, it has to be very thick. And if you just extended what has been done in the past to make bigger mirrors, then they really wouldn't work. They'd just be too heavy and too unmanageable. So you had to do something radical to make a big mirror. And our solution has been to sort of take all the weight out of the mirror by honeycombing the inside. So if you do something different, then you can make them bigger.
Could you tell us just how you make these mirrors using the spin method?
Well, there's two important things that we're doing. The idea of spinning is very simple. If you take a pool of liquid, whether it's water or glass or whatever, and you spin it around, then the liquid gets thrown to the sides, and so you form the dish shape that you want for a mirror. But actually, that's fairly easy to do. It just means building a furnace that spins, which is what this one does. But the more difficult problem we had to solve is to make honeycomb structure. So there are two things going on at once when we make the mirror. We spin the liquid glass. We also fill the liquid glass with blocks of material that will later be removed to make cavities. And it's learning how to do that that's actually been more difficult.
Because this mirror is about 2 feet thick, isn't it?
Yeah, it's actually about 2.5 feet thick. And of that thickness, 80% of it is air. So if we melted it, it would actually only be 6 inches thick.
Of course, the Europeans in particular are making very thin mirrors now, but you haven't gone along that way.
No, if you haven't developed a technique to make the honeycomb structure, then your only option is to make a thin, solid sheet of glass, and that's what the Europeans are doing.
When the mirror is being spun, the temperature goes up to well over 2,000 degrees Fahrenheit, and that must cause problems. How long does it take to cool down?
Yeah, to be precise, we heat to about 1,200 degrees centigrade, which is 22 or 2,300 Fahrenheit. We get to that temperature rather quickly in 2 or 3 days. The cooling takes a long time because you must cool glass very slowly, otherwise it cracks. So we slow the cooling rate down to just 2 or 3 degrees a day as the glass freezes.
But so far, everything seems to be going very well.
Yep, this one has just come out beautifully, and there are two big hurdles. One is whether the mold would come apart, all those blocks which are held below the surface, and if something breaks, then they'll just bob up. So when we were watching the melting, we were watching very carefully to make sure none of those 1,000 blocks had bobbed to the surface. So that worked. And then during the cooling, if you make any mistakes, you'll crack the mirror. And the fact that it's come out now with no cracks, I mean, we got that right.
Now that the mirror's out of its mold, what's the schedule from now on?
Well, in a few weeks we'll lift it, and we have to set it vertical, so we lift the mirror up, put it in a stand, and then turn it vertical. And then we go in from the back, and all these blocks of material that have made the honeycomb structure, we remove all that material so as to get left with the lightweight honeycomb.
I gather the next step is to make an 8.5 meter mirror. Are you going to change anything particularly for that, apart from the sheer size?
No, I think basically everything that we've made is now sized for the full 8.4 is the biggest we'll make. So I think we'll pretty much do things the same. It'll use more glass. We may heat it a little longer, but it's basically the same thing now.
How do the mirrors you're making by these methods compare with mirrors made by more conventional methods?
Well, there is no conventional way to make an 8-meter mirror. So you could try and make a conventional piece of glass, if you like, is thick and solid. And if you made a mirror even of this size, solid, it would weigh 60 tons as opposed to the 10 tons of glass that are in this mirror.
And you'd have thermal problems too, wouldn't you?
Yes, I mean, not only is it very heavy and unwieldy, but the glass it takes a very long time to come to the same temperature as the air. And one of the great problems with present large telescopes is that the mirrors aren't at the same temperature as the air, and if they're a little warmer, then you get convection off the surface, and that convection makes the image shimmer. So the very thing you're trying to do with a big telescope, which is make the sharpest possible image, is spoiled by the heat that's stored in a thick piece of glass. So that's one of our big incentives to make honeycomb, was to overcome that problem.
What's the general time scale for making a large mirror like this and installing it?
Well, the typical time scales, I think the Palomar 200-inch, for instance, was probably about 14 years. Well, in fact, the blank, I think, was cast in 34, and the telescope came online in 49. The 4-meter telescope on Kitt Peak took 10 years from the melting of the blank to putting it in the telescope. And the one of the 3.5-meter mirrors that we finished, the one that we finished last, will be about a 3-year cycle from when you start the melting to when you actually start using it in a telescope. So it's a lot quicker now than it used to be. Replacing 6 smaller mirrors with one huge mirror does pose extra problems.
The observatory building on Mount Hopkins was designed especially for the MMT, so clearly there will have to be modifications.
There are a number of modifications that we will have to carry out, not only to the building itself, but some to the mount of the telescope. The mount itself, we have begun that modification this summer. It involves stiffening the azimuth bearing, and we had to insert a giant new bearing in the azimuth axis, and that has now been complete. We are using our so-called monsoon season as the time to do these modifications to the facility, so that we can keep the MMT running in its current form as late as we possibly can, so that we won't be out of operation so long when we convert it to the larger telescope. The next summer, a year from now, the building itself will be modified, and the two giant doors that you see to the building behind me will be removed from the building and have shims about 6 feet long put to raise the building by 6 feet and to extend it outward by 6 feet. That's because the new telescope tube, if you will, for the 6.5 meter telescope is longer than that for the existing MMT, and we need the extra space to allow us to swing the telescope inside the building. So that will be a major modification that will happen next summer. And then, of course, the big modification is when the entire optics support structure, the silver-colored structure behind me of girders, gets lifted out of the telescope bodily and replaced by a different one that holds the 6.5 meter mirror.
One point occurs to me. The road up here is pretty rough in places. Isn't getting the large mirror up going to be rather a problem?
Yes, it is going to be a problem getting the mirror up the road. What we plan to do is to bring it from Tucson to the base of the mountain, lying on its back on a flatbed truck, and then turn it vertically to bring it up the winding mountain road.
When do you expect the telescope to be in operation with this new mirror?
Our current schedule calls for the mirror to be installed sometime late in 1995 or early 96.
What are going to be the main advantages of using the new mirror over the existing 672 inches?
I think the main advantages, there are two of them that one should cite. One is the simple collecting area increase that we gain, more than a factor of 2 in light gathering power of the telescope, meaning that we can see things twice as faint as we could before. And secondly, the new large telescope will have a much wider field of view than the current MMT. 1 degree compared to 3 arc minutes. And in terms of area of the sky that you can cover, that means we're looking at 400 times as much area of the sky at once as we do with the current MMT.
Incidentally, what are you going to call it? It's no longer going to be a multiple mirror telescope.
Actually, it will be an MMT. We just are not sure what the acronym will stand for anymore. We're open to suggestions for what the 3 letters should stand for. We would like to keep our same acronym.
Up to now, the last really successful casting of a giant mirror was that of the Palomar 200-inch reflector, as long ago as 1934. If Roger Angel's honeycomb and spin method is as successful as we've every reason to believe, then giant mirrors can be developed to the full, and eventually, no doubt, used in space and even on the surface of the moon. It's an exciting prospect. And in looking at the new MMT, we really are looking at a telescope of the 21st century.